तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last class we started our discussion on ECL gates and we have seen how the circuit functions. So, we shall carry on with the discussion. So, today's class what we shall do is we shall take up the circuit of a commercially available ECL gate. Okay. So, I have it on the blackboard here. Okay. So, this is the circuit diagram of a commercially available ECL gate. This is the ECL 10K series. Okay. And we shall analyze this circuit. Okay. And we shall see how the input output characteristics are, okay, for this particular circuit. All right. So, let us just look at the circuit and see how it is, how does it compare with the circuit which we have already discussed. Okay. Well, this circuit, as you see here, this part of the circuit, okay, this is the emitter coupled configuration. You have the transistors T2 on one side, and at the base of that you have the reference voltage. So, this is basically the VR, the voltage here is the reference voltage, okay, and this T1 and T3 are the transistors, okay, for the inputs, where the inputs are applied, okay. And from the collectors of these transistors you are supposed to have the emitter followers, okay. So, you have the emitter follower transistors here. I just sorry, I missed out something here. Okay, you have some resistances here at the inputs. Okay. So, these resistances are 50 kilo ohms. Okay. All right. So, so at the collector of these transistors, these are the emitter followers, okay, transistors here. So, this is T5 this side and T6 on the other side. Okay. You see that the resistances are missing. All right. The output is taken at the emitter, but the resistance is missing here. Okay. Now, if you are taking this output directly, you can externally connect a resistance of whatever value you want to choose, because also that contributes to the delay also, what is the value. But if you are feeding it feeding this output to the input of another ECL gate, okay, you see what you have here is at the input A you have a resistance. Okay. So, this particular resistance would act as the resistance for this emitter follower. Okay. So, this particular is, if you are feeding output of a similar gate to the input of this gate here, okay, you have this transistor which will, the emitter of which will come here. So, this resistance acts as the emitter follower. Why you have a resistance here at the input is, one reason is that if you have a resistance, the base is basically connected to the lower potential here. So, if any input is left floating, okay, it will be basically a low voltage, okay. It will be a logic 0 at the input, okay. You are basically not leaving the input floating, which can give rise to lot of problems, okay. You are if you are not connecting an input here, okay, the input which will be at that the logic at that particular input is going to be a logic 0, okay, because that is basically connected to the lower potential through a resistance, okay. And if you are having a or a NOR potential, or NOR logic, you know that if any input is logic 0, it actually does not contribute to the output. Okay. The output is going to be governed by the other inputs. Okay. If you have a 3 input NOR gate or OR gate, okay, if one logic is 0, then the output is depends on the other 2 inputs. Okay. A 0 does not contribute. On the other hand, all right. Whereas in a NAND or AND configuration, okay, a 1, if you have any input as 1, okay, the output does not depend on that input, but it depends on the other inputs. Okay. All right. Any 0 is going to force the output to 1 in a NAND or AND, in a NAND, okay, whereas in a NOR any 1 is going to force the output to 0. Okay. Anyway, so that is why you have a resistance at the input, which is basically means that any input which is not used, okay, unused input, okay, is has a logic 0. All right. The other interesting thing here is okay, well, this part of the circuit, okay, I just which I am marking out here. Well, this part of the circuit is for generating the reference voltage. Okay. You do not have a separate voltage input for reference voltage, okay, but this is generated internally in the chip, okay, from the power supply. Okay. So, this part of the circuit generates the reference voltage. So, we shall discuss that. Okay. The other interesting thing about this circuit is that you have 2 ground connections. Okay. Normally you have one the 2 terminals for the power supply, but here you have 2 ground connections. The reason for that is like this, that you see, well, if you look at this part of the circuit, okay, for example, this T1 and T2, okay, what is happening is when the input changes, okay, the current may switch between one branch from one branch to the other, but the total current remains more or less fixed. Okay. All right. It is just this the total current which is being switched from one branch to the other. Okay. And also, of course, if for this reference voltage generation circuit, the current is almost fixed. Okay. So, if you look at the circuit connected to this ground 2 in this case, okay, this one, okay, the current flowing is almost fixed. Okay. Whereas here ground 1 is actually connected to the external the transistors T5 and T6, okay, which is connected to the output, and output you may have, for example, large capacitive loads. Okay. And so what happens is when the output voltage switches okay, from one state to the other, okay, and you know in an ECL gate it is supposed to be a very fast logic. Okay. So, dV/dt or the rate of change of voltage is going to be very fast. Okay. So, you are liable to have large current spikes, okay, along this across these transistors, flowing through these transistors, okay, and again which may give rise to variations in the power supply, as we have already discussed. Okay. So, this ground 1, okay, is sort of considered to be the noisy ground, okay, and ground 2 is considered to be the clean ground. Okay. So, basically what is done is the 2 grounds are separated, okay, so that the effect of any variations in power supply voltage is not felt in this part of the circuit, okay, which is actually carrying out the logic. Okay. So, you have 2 separate grounds, and well, they may be connected finally at the system level, but at this stage they are separated out, okay, and to protect this part of the circuit from any noise as such, all right, which may give rise to glitches in the logic. Okay. So, that is the other thing, ground 1 and ground 2. Okay. So, with this background we can start our analysis of this circuit and see how the input output voltage characteristics looks like. Okay. all right. Okay, so first let us see what is the value of VR, what is the reference voltage, okay, that is what we must find out. Okay. VR or the reference voltage from this circuit is the base voltage of T4 minus the VBE of T4. Okay. VBE of T4 or any transistor here, let us call it V on, and okay. So VB4 minus V on, okay. Okay, V on is the base emitter drop of a transistor, okay, when it is in the on state, okay, and this let us say V on is around 0.75 volts in this case, okay. Okay, so we have to find out VB4. What is the value of VB4? It is very easy to calculate, okay. The total drop from across the power supply is 5.2 volts, out of which 1.5 volt is dropped across the diodes, okay. The remaining voltage is dropped across the two resistances and the constant current flowing through that, okay. So we can find out the current, okay. Once you find out the current, you can find out the drop across this 900 ohms, and that is, this is ground, so minus of that, okay. So VB4 is equal to 5.2 minus 1.5 is the drop across the two resistances, okay, divided by the sum of the two resistances is 5K plus 0.9 K. So this gives the current in milliamperes, okay, and the drop across the 9K 0.9 K is going to be this, all right. So this is the drop across that resistance, minus of that is the voltage at VB4, okay. So this, if you calculate it, it gives minus 0.57 volts, okay. So VR is equal to minus 0.57 minus 0.75 is equal to minus 1.32 volts, okay. So that is the value of VR, okay. Now that is, once we have calculated, we can go ahead. Now we shall look at the two different states, that is, one is when the left branch is conducting and the other is when the right hand branch is conducting, okay. So let us say one case 1, T2 is on and T1 and T3 are off, okay. That is, the right hand branch is conducting, okay. T1 and T3 off means that the input voltages at the base of T1 and T3 are much less compared to VR, okay. We have already seen that in fact a very small difference in voltage, okay, is sufficient to transfer the entire current to the right hand side branch, okay. So if it is less than VR by even as low as 0.75 millivolts, okay, very little current would flow in the left hand branch and most of the current would flow in the right hand branch, okay. So what is the value at this point? This is, let we call it VE, okay, that is the emitter voltage, that is the common emitter point of these transistors, okay. When this is conducting, VE is equal to VR minus V on, okay. So that gives us minus 1.32 minus 0.75 is equal to minus 2.07 volts, okay. IE, that is the total emitter current, okay, is the difference between these two voltages divided by R, okay. The power supply voltage is 5.2 volts, okay. So you have 5.2 minus 2.07 divided by 780 ohms. Okay, and it works out to 4.02 milliamperes according to my calculations. Okay, almost 4 milliamperes. Okay, all right. So, this is the emitter current which flows here. So, these two transistors are not conducting. Okay. Now, if you assume that well, this is the collector current. So, the beta is high, the collector current of that transistor is equal to the emitter current. Okay. So, the collector current of this transistor, collector voltage, okay, Vc2, okay, that is the collector voltage of transistor T2, Vc2 is equal to minus IE R2, if I call this R2, okay, this is R1 say and this is R2, okay, which is 245 ohms. So, if you do this calculations, okay, 4.02 milliampere into that into 245 ohms. So, this gives minus 0.99 volts. Okay. So, the same current is flowing through this. So, the voltage at this collector point is this. Okay. And okay. Now, just for the sake of checking, you know, this is the collector voltage, all right, and what is the emitter voltage? Minus 2.07. Okay. So, what is VCE of this transistor, of the transistor T2, say VCE2 is 2.07 minus 1.99. So, it is 1.08 volts. Okay. So, which means that this transistor is in the active region. Okay. All right, it is not in saturation, that is, it ensures that. Okay. All right. Now, we know Vc2. So, what is V output? VO2 minus 0.99 minus 0.75 is equal to minus 1.74 volts. So, that is the output, okay, when in this condition, okay, that is T2 is on and T1 and T3 off. And what is the output at VO1? Okay, VO1 is the output at here. Okay. Now, this output is going to be, so this, there is no current flowing normally. Okay, that is basically IC1 is 0. There may be a current flowing which is the base current of T5. Okay. All right. So, that is going to be the current, the emitter current of T5 divided by beta times, okay, beta plus 1 times. Okay. So, it is the basically it is going to be 0 minus, okay, R1 times the load current divided by beta. Okay. Okay. So, that depends on the load current. All right. Now, for we may assume, okay, sorry, there is minus 0.75 is the drop across beyond, minus 0.75 minus this 0.75 is the drop, the base emitter drop of this transistor T5. Okay. So, 0.75 minus, so let us assume this is minus 0.9 volts. Okay. Just assumption, okay, that this is the value of IL is such that this is this is 0.15 volts and you have VO1 is minus 0.9 volts. Okay. In fact, this has been designed assuming this, all right, in which case what you have is VO1 plus VO2 by 2 is equal to, what is VO1? Minus 0.9 and VO2 is minus 1.74 by 2. What is this equal to? Equal to minus 1.32 volts, which is equal to VR. Okay. That is, the output voltage swing is symmetric about the reference voltage. Okay. That is, the output voltage of this ECL gate is also going to be the input voltage, okay, because the output is going to be fed in as input to the other gates. Okay. So, the input voltage swing is symmetric about the reference voltage, that is what is important here. Okay. So, you get this voltage variations. So, also okay, all right. Okay. So, this is about the case where T2 is on and T1 and T3 is off. Okay. Now, let us take the other case, okay, that is T2 is off and T1 or T3 is on. What is going to happen? Okay. That is case 2, T2 is off and T1 or T3 is on. Okay, that is the base voltage for transistors T1 or T3 is greater than the reference voltage, okay, which would mean that either T1 or T3 is on, whereas T2 is off. Okay. So, if you have this condition, IE1, say T1 is on, so IE1 will be equal to, what is the T1 is on means, okay, that the input voltage at the base of T1 is equal to the input corresponding to logic high, okay, and we have seen that the voltage corresponding to logic high is minus 0.9 volts. Okay. So, let us assume that at the input you have the input voltage is minus 0.9 volts. Okay. So, the logic levels, the voltage levels here, the logic levels are minus 0.9 and minus 1.74 volts. Okay. Minus 0.9 is logic high, minus 1.74 is logic low. Okay. So, if you assume that it is minus 0.9 volts, so what is the current flowing? Okay. So, the difference between 5, what is the VE in this case? The emitter voltage in this case, if this is minus 0.9 volts, the VE is going to be minus 0.9 minus 0.75. Okay. So, this is minus 5.2. So, the current flowing, okay, is going to be 5.2 minus the sum of minus 0.9 and the 0.9 and 0.75. Okay. So, divided by the resistance. So, you have 5.2 minus 0.9 plus 0.75 divided by 0.78 kilo ohms. So, this comes in milliamperes is 4.56 milliamperes. All right. All right. So, that is the current which is flowing. Okay. Now, what is the output voltage? What is the collector voltage going to be? VC1 is going to be 4.56 into 220 ohms. Okay. So, this gives 0.22 basically. So, this is milliampere, so this is kilo ohms. So, this is going to be 1 volt. Okay. So, VC1 is minus 1 volt. Okay. All right. So, this is the drop across that resistance. So, VC1 is minus 1 volt. Okay. And VO1 minus 1.75. All right. It's almost the same as the previous case, and VO2 similarly is going to be minus 0.9 volts. Okay. because in this case again there is no current flowing in the other branch here. So, this drop is 0, again the output is going to be this drop, and again depending on the load current, okay, you get the output. So, we assume that this is the voltage. So, basically you see that both cases, all right, this is true. So, the output voltages vary from minus 0.9 to around minus 1.7475 volts. Okay. Now, can we draw the input output characteristics based on this? Okay. All right. I should remove this. So, this is the input scale, say. Okay. I draw this. This is VR is equal to minus 1.32 volts. Okay. And then what happens? So, suppose we are plotting the OR output. Okay. Now, for the OR output, when the input is low, output is also low. Okay. So, when the input is low, okay, the output should also be low, okay, and then it goes high, all right. Now, so when the input is low, what is the output voltage? That is the equal to logic low, minus 1.74 volts, correct. So, this is going to be minus 1.74 volts, okay. This is minus 1.74 volts, okay. So, this goes like this, then up to what value does it go like that? The logic changes, we have already seen that, okay. The current is going to switch from one state to the other, okay, or one branch to the other, when the input voltage is about 75 millivolts from the reference voltage, okay. So, when it is very close to this, okay, so if then it starts changing like this, it just switches to the other level, okay. Okay. So, what is this value here? It's around minus 0.9 volts, okay. So, this is OR. All right. So, it goes from minus 1.74 to minus 0.9 volts. What about the NOR? NOR voltage. So, basically in the case of NOR output, again when the input is low, the output is going to be high. Okay. So, here the output is going to be high. All right. So, what happens is, what is the value here we have seen? Again minus 0.9 volts, and then it goes like this, okay. But there is a small difference here, okay, between the two. This you can see when you go back to this circuit, okay. See, when the input voltage goes high here, okay, what is happening? This particular transistor is off, okay, T2 is off, say T1 is on, okay. Then what happens is, this circuit behaves as an amplifier. You have a collector resistance R1 220 ohms, and you have an emitter resistance 780 ohms, okay. And if you go on increasing the input voltage, what is going to happen? What happens is, if you go on increasing the input voltage, what happens to this VE? It also keeps on increasing. So, what happens to the current? Current also increases, emitter current keeps on increasing because VE increases. So, the drop across the emitter resistance increases, which means that the emitter current keeps increasing, which also means that the collector current is also increasing, because collector current is the same as the emitter current, okay. So, what happens to the collector voltage? collector voltage decreases because the drop across this collector resistance increases. So, as you go on increasing the input voltage, the emitter voltage increases whereas the collector voltage decreases. So, what happens to VCE? The VCE goes on reducing and ultimately the transistor will go to saturation, okay, when this VCE becomes about 0.2 volts. Okay. So, in this case the transistor is actually going to go to saturation if you go on increasing the input voltage, because the VCE keeps on reducing. This is just like a common emitter amplifier with a emitter resistance. Okay. So, what is the value of the input voltage when this transistor goes to saturation? Okay. Can we find that out? Okay. Say when VCE is 0.2 volts, say when VCE 1 is equal to 0.2 volts, IC is equal to IE. What is the value? The total voltage from power supply across the power supply is 5.2 volts. 0.2 volts is dropped across the transistor. The remaining 5 volts is dropped across the two resistances, okay, and the current flowing through the two resistances is the same, IC is equal to IE. Okay. So, 5 volts divided by the sum of these two resistances is the current. Okay. What is the sum of these two resistances? 780 ohms plus 220 ohms, 1 kilo ohm. Okay. So, IC is equal to IE is equal to 5 volts by 1 kilo ohm, which means 5 milliamperes. Okay. All right. So, what is VE equal to? V is equal to 5 into 780 ohms. Okay, I think we put 0.78 because this is in milliamperes, this is in kilo ohms, minus 5.2 volts. Okay, that is the reference. Okay, plus this drop. Okay, so that is VE. So what is this? This is 3.9, I think, minus 5.2 minus 1.3 volts. Am I correct? All right. Now V is minus 1.353 volts. So V in is minus 1.3 plus 0.75. Okay. So that is equal to minus 0.55 volts. Is correct? All right. So when V in goes to minus 0.55 volts, okay, the transistor actually goes to saturation. Okay, and once it goes to saturation, okay, so what is going to happen is after that, so basically, okay, once it goes to saturation, what happens is if you go on increasing the input voltage, okay, the VCE remains fixed, it is not changing anymore. So if you go on increasing this, the emitter voltage goes up because the drop across this is 0.75, which means that the collector voltage also is going to go up. So basically the characteristics which you have now is going to be something like this for the NOR output. It behaves like this, goes up like this. Okay. So this is minus 0.55 volts. Okay. All right. Well, we have already seen that when the input voltage is minus 0.9 volts, okay, for this output, the output voltage is minus 1.74 volts. So this, when this is minus 0.9, this is minus 1.74 volts. Okay. So, this point we have already seen calculated. Okay. So, it goes through this point, goes down to minus 0.55 and then goes up. So, this is the NOD output. Okay. Well, so the point is, as we see, the transistor actually goes to saturation if the input voltage is very large, but the point is the input voltage has to be restricted, voltage range has to be restricted. Okay. That is, the input voltage range which we must have, okay, it must be restricted to minus 1.74 volts on one side and minus 0.9 on the other. Okay. So, if the input voltage range is restricted within this limit, okay, then it is we will be sure that the transistors are not going to go to saturation. So, that is another condition, okay, which we have already seen last class, that we have to restrict the input, like we had said VR plus minus half V on. Okay. So, similarly, here also we have to restrict the input voltage within a certain limit, that is, the input voltage should we have assumed here that the input voltage range is the same as the output voltage range, and if this is adhered to, then the transistors are not going to go to saturation. So, they remain within these limits. Okay. All right. Now, okay, for this circuit, what is the noise margin? Let us take it up. Okay, the next thing, from the input output characteristics, you can calculate the noise margin. Okay. The noise margin low is VIL minus VOL. So, what is the input low in this case? So, it is with respect to VR. So, basically if the input voltage is up to here, it was going to be considered a logic low. Beyond that, it is no longer a logic low. Okay. So, this is VR, this is the reference voltage. Okay. All right. It is this is the reference voltage. So, this point, okay. So, what is this difference in voltage? Yeah, usually it is 0.75 as we had seen from our calculations, but for worst case, okay, because of the other drops in the base emitter, series resistance drops and all, this is usually taken to be 0.1 volts, okay, for the worst case. So, if this is 0.1 volts, that means this is how much? Minus 1.22, all right, and the other extreme is minus 1.42 on the other side. So, anyway, so and V output low is minus 1.74. So, it is minus the difference of sorry, this is minus 1.42, sorry, this is minus 1.42, that other side would be minus 1.22, sorry. So, this is going to be 1.74 minus 1.42, okay. So, this is 0.32, okay, and noise margin high is equal to VOH minus VIH, so which is equal to minus the difference of 1.22 and 0.9. So, this is again 0.32 volts. So, basically you have equal noise margins, low and high. Okay. Okay. So, 100 millivolts above V reference would be considered a logic high. Okay. It would that particular branch would start conducting. okay, if the input voltage is greater than VR by 100 millivolts. Okay. So, that is minus 1.22, and the logic high output is 0.9 volts, minus 0.9 volts. So, the noise margins are symmetric in this case, okay, of 0.32 volts. All right. Okay. So, we have made the calculations of noise margin from here. Okay. Then the next thing which we shall take up from this circuit is power dissipation. Okay. All right. I think I can remove this now. Okay, power dissipation. Okay. We have seen that in the two states, okay, that is one state when left branch is conducting and the other state when the right hand branch is conducting, the values of the currents, i.e., in one case current was 4.02 milliamperes and the other case it was 4.56 milliamperes. Okay. So, we can take the average of the two currents, i.e., average as of these two, okay, and that is equal to 4.29 I think. Okay. And power consumption will be equal to this current 4.29 milliamperes into 5.2, okay, in milliwatts, okay, and this works out to 22.3 milliwatts. Okay. Okay. For the reference power supply, for the reference voltage circuit, okay, reference voltage generation circuit, okay, what is the current through T4? I should say i.e. T4, say the reference voltage divided by 6.1 K is going to be that current, okay, all right, that is the current which is flowing in through this branch, okay. So, that is okay, the difference, reference voltage and the supply. So, 5.2 minus 1.32, that is the drop across that resistance, divided by 6.1 K, that is equal to 0.64 milliamperes, okay, and bias, okay, that is the other part, this one, okay, one can easily calculate, okay, we know this voltage, all right. So, the current flowing through this is the well, if you know the voltage, this is ground. So, that is the drop across 900 ohms divided by 900 ohms gives the current, okay. So, we have already seen that the base of T4, the voltage is 0.57 minus 0.57 volts. So, 0.57 divided by 0.9 K, so this is 0.63 milliamperes. So, the power consumption is 5.2 volts into 0.64 plus 0.63 is equal to 6.6 milliwatt. We just make this calculation, okay. Now, okay, in this circuit, this OR NOR gate is available as a quad OR NOR gate in a chip. Okay. That means that in a chip you have 4 such OR NOR gates, okay. And this part of the circuit, the reference voltage generation circuit, is common to the 4 gates. Okay. You do not have the 4 different reference voltage generation circuits. You have a common reference voltage circuit for the 4 gates. Okay. So, now how do you calculate the power dissipation per gate? Okay. So, the power dissipation is going to be 22.3 milliwatts plus 6.6 divided by 4, because the 6.6 milliwatts is shared in the 4 gates. Okay. So, this works out to 24 milliwatts per gate. All right. And so, this is the power dissipation, okay, per gate, which is rather high, okay, which you can see. That is one of the problems of ECL gate. The power dissipation is rather high, because the transistors have to be operated in the active region, okay, which means that you cannot restrict the current. Okay. I mean, all right. So, you have a large current flowing. Okay. All right. So, that is why the power dissipations are rather high. Okay. So, you have 24 milliwatts per gate. Okay. In fact, for this particular circuit, the delay, okay, is 2 nanoseconds, okay, per gate, which makes a power delay product of 48 picojoules. All right. So, for this gate, the delay is 2 nanoseconds. So, the power delay product is 48 picojoules. Of course, one must remember that this is the first generation of ECL gates. Okay. So, you should not compare with the second generation of TTL gates. Schottky TTL is, advanced Schottky TTL is faster. Okay. But you should not compare, it is unfair comparison. Okay. You should because this is actually the first generation, we will come to that next generation, okay, characteristics, which is superior to advanced Schottky TTL. All right. So, this is the characteristics of this particular gate. Okay. Just before I close today, I just have one small question. Okay. This, if you look at the reference circuit, okay, it is a bit peculiar. We have 2 diodes here. Okay. Why do we have 2 diodes there? What is the purpose of having 2 diodes? No, it is not really level shifting. Okay. It is basically for temperature compensation, correct. See, you know that the base emitter voltage of a transistor, okay, changes, okay, it is at around 2 millivolts per degree centigrade. Okay, and when you convert that to current, because of the exponential nature, you have a lot of difference. Okay. So, what happens is when the temperature goes up, you see the voltage across these diodes also changes. Okay. So, from this point, if you see, you have 2 diodes here, and these are the 2 base emitter voltages here. Okay. So, this these presence of these diodes actually compensates, okay, for any change in the voltages across the base emitter of these transistors. Okay. So, you do not have any problems, okay, as such. So, these diodes are used for temperature compensation. So, otherwise you could have had a simple potential divider type of network. Okay. So, I think we shall stop here today. What we have seen today is we have gone through, we have analyzed this particular circuit, which is the 10K series. We have looked at the input output characteristics of an ECL gate, okay, as well as the noise margins and the power dissipation. Of course, the problem is power dissipation, which is quite large. Okay. The next class what we shall take up is the next series of TTL gates, ECL gates, and we shall also see the efforts being made to improve the characteristics further. Okay.